right, so today we're going to start section 6.5, which is on basically right triangle trig. So the idea of right triangle trig is they give you a little bit of information, and they ask you to find out other pieces of information about the triangle. How long are the sides? How big are the angles? Okay, that's kind of the goal of what we're going to do. So as I said before, we're going to be doing this with right triangles. Okay, so a right triangle is any triangle that has a 90-degree angle. And when you're working with a right triangle, it does make it a little bit easier because, one, you already know one of the angles. And two, there's other theorems you can use when you have right triangles. Anybody know another theorem that applies to right triangles? The Pythagorean Theorem. Okay? That theorem is, you can use it, but only with right triangles. When we study non-right triangles, I think it's in chapter, it's either 7 or 8, we can't use that theorem, so we've got to use something else. Okay, the side that's across from your right angle, that's the hypotenuse. The two other sides in a right triangle, those are the legs. So here's a diagram. I've labeled the sides using A, B, and C, because when you see in a second our Pythagorean theorem, those are the letters we generally use in that theorem. But you could use X, Y, Z. It doesn't really matter. Okay, once you draw a right triangle, the two other angles have to be acute. How come? In a right triangle, why do the other two angles have to be acute? At least in a flat triangle. If you start talking about like spherical geometry, all these rules change. But we're talking about triangles that are flat, not spherical.
Because if they were bigger than 90 degrees, it wouldn't close.
Yeah. All the angles here have to add up to 180 to make that a closed three-sided polygon. So if one angle is already 90, the sum of the other two has to equal 90. So you could have one angle that's like 89.9 and then the other one that's 0.1. But you can't go any higher than 90. It has to be less than 90. Okay. And in a right triangle, this is a theorem that we can use, the Pythagorean theorem. What is the Pythagorean theorem? What does that say? Yeah?
A squared plus B squared equals C squared.
Okay, can you explain to me what that means?
If you add the two, if you square both legs and add them, it equals the square of the hypotenuse.
Perfect. That's exactly right. That's the Pythagorean theorem. We normally write it with the letters A, B, and C, but just saying A squared plus B squared equals C squared, that's not the theorem. That's maybe how you represented it. But the idea is you square each leg, you add them up, and it equals the hypotenuse squared. Okay, whatever you want to name your legs and hypotenuse. Okay, if we have some time at the end, I'll go through a proof of the Pythagorean theorem. This is one of those theorems. There's just like over 100 different ways to prove it. The ones that I like are visual. You look at pictures and you can prove it. And it's a pretty straightforward proof that requires nothing more than knowing the area of a triangle and algebra 1. That's it. It's pretty easy once you draw the right diagram. Okay, so if we have time, we'll look at that at the end. Okay, let's take a look at our 6 trig functions. So I heard some people saying a word
Sohcahtoa.
earlier. Yeah, Sohcahtoa. In some of my classes, people confuse it with Sacagawea. I was like, no, that's something different. I've had that a couple times.
Lewis and Clark.
Yeah, that's explorers, Lewis and Clark. Yeah, different stuff. So Sohcahtoa is it's an acronym to try to remember what I've written right here. If you think about it, let me try to put it down here. Okay, sine is opposite over hypotenuse, SOH. Cosine is adjacent over hypotenuse, C-A-H. Tangent is opposite over adjacent, T-O-A. Right, so it's kind of a quick way to try to remember those trig functions. Okay, once you have those three, how do you get the other three? You can basically take each one of those and find the word for it.
So you just do the reciprocal.
Yeah, they're the reciprocals. Okay, we've studied that when we looked at trig identities a little bit. But the idea is that you just flip them. So cosecant is hypotenuse over opposite, secant is hypotenuse over adjacent, and cotangent is adjacent over opposite. So opposite and adjacent are what we call relative terms, meaning they can change depending kind of on which angle we're looking at in the triangle, like left and right. Okay, left and right change depending on which way you face. For some people, this might be right and that's left. For me, that's reversed because I'm facing here. That's left and that's right. So we have to be careful what angle we're looking at. So if we're looking at that angle, okay, the opposite side in that triangle means opposite from that angle. Okay, so opposite is the side that's farthest away. Okay, it's the side that if you got rid of it, you'd still have an angle. That side has nothing to do with forming that angle. It's farthest away. Adjacent, that's the side that's next to the angle. Some people say, well, wait, isn't there two? Yes, but one of them is the hypotenuse. So hypotenuse is always across from the 90. So it's not that one. This is the adjacent. It's the side that forms the angle. It's right next to it. And it's not the hypotenuse. Okay, now if you switch where theta is, what do you think happens with opposite and adjacent? Yeah, they switch places. So if we put theta up here, it's kind of like changing which way you're looking. Now like left and right changes. So now this is opposite because it's farthest away. Adjacent is the side that's next to it. And the hypotenuse is always across from the 90. So any questions on that idea? Opposite and adjacent are relative terms. So if we have two right triangles that are congruent, have congruent angles, then we can say that those triangles are similar. Okay, from geometry, that's called angle-angle similarity. If you've got two triangles, two right triangles, okay, you already know that they both have 90s, okay, because they're both right. And if you know that the other angles are that match, basically what that means is one triangle could be a larger or smaller version of the other. Right? Just knowing all the angles doesn't tell you the size of the triangle. Okay, think of an equilateral triangle. If I said to you, what are the angles? Okay, hopefully everyone could get that. That's an easier question. But if I said, how big is an equilateral triangle? How big do you want it to be? You could have all the sides 10, 10, 10, 200, 200, 200. Okay, just knowing the angles doesn't tell you anything about the size of it. But it does tell you that shapes are similar. So my point here is that the previous trig functions always have the same value for a given theta. Okay, so let's suppose you have a 30, 60, 90 right triangle. The size of the triangle doesn't affect the sine, the cosine, the tangent, the secant, the cosecant, or the cotangent. The sine of 60 is always the same, regardless of the size triangle that it's in. Size here doesn't make a difference. All right, so to show you numerically, in this problem, the sine of 60, sine is opposite over hypotenuse. Opposite is square root 3. Hypotenuse is 2. Okay, let's find the sine of 60 in the bigger triangle. Opposite is 2 square root 3. Hypotenuse is 4. So at first they look different, but what do the top and bottom on the right-hand fraction have in common? Could you reduce it by?
Your factors of 2.
Yeah, by 2. 2 goes into 2 once, 2 goes into 4 twice. You get the same thing. Okay, so any question on that idea? The size of your actual triangle has nothing to do, has no effect on the trig functions of the angles. Okay. You could try that with all 6 if you wanted. All right, so let's say that I gave you one of the trig functions, 1 out of the 6. I could give you any one of them. And I want you to figure out the other 5. What am I basically giving you? If I give you 1 out of the 6 of these trig functions, what do you know? Yeah?
You're basically giving us one of the sides.
Close. I'm giving you more than that. Yeah.
2 of the sides?
I'm giving you 2 of the sides. So if I said to you the sine of an angle is 2/3. 2/3. Opposite is 2. Hypotenuse is 3. You now know 2 out of 3 of the sides.
Oh, and then you can do Pythagorean theorem.
Yeah. And now you could use the Pythagorean theorem to get the remaining side that you don't have. Right? So if I give you a trig function, label what you're given, use the Pythagorean theorem to get the third side. Now you know all the sides. And you can find any trig function you want. That's kind of the point there. But it turns out you don't even need to know the angle to find trig functions. All you need is the sides. If you're going to plug it into a calculator, you need the angle, like sine of 60, and hit enter. But I could just give you a picture, like the last problem we just did. I could erase all these angles. And I could just call this angle theta. And say the sine of theta is square root 3 over 2. You don't need to know what theta is to find the sine of it. Okay? And that confuses people sometimes. Okay? You don't need to know what theta is to find any of the 6 trig functions. Okay? And kind of an analogy to that is if you met somebody and you didn't know their name, does that prevent you from describing things about them that you can see visually? No. I don't need to know someone's name to describe the color of their shirt, the color of their eyes, their hair, things like that. Right? Same idea here. You don't need to know what this angle is to describe things about it. Specifically, we're describing these 6 things about it. Okay? Does everybody have what's on the left? All right, so what we're going to do is take a look at 1a. It says let sine of theta equal 5/6. I didn't even tell you what the angle is. I want to know all the other trig functions. Now, could I find the angle? Sure. Or at least I could narrow down which quadrant it's in. If all you told me that the sine was equal to 5/6, That angle could be in quadrant 1, it could be in quadrant 2. The size of the angle. Now, if you tell me we're talking about a right triangle, well, that narrows it down then. Quadrant 2, the angles are bigger than 90. You're not going to get angles bigger than 90 here. But my point is, if you graph that in y1, graph that in y2, you're going to get 2 answers if you try to find theta. Right, so we're not quite there yet, but when we do find it, it's not going to be hard for us to eliminate one answer, because all the angles in a triangle have to add up to 180. So only one of the 2 answers will work for our application. All right, so let's write down what our 3 sides are. Okay, somebody tell me one of the sides I know right away without any work. Yep.
The opposite is 5.
Opposite is 5. How about another side?
The hypotenuse is 6.
Sure. So if in your head you have trouble visualizing how to set up the Pythagorean theorem, draw it out. Doesn't matter where you put theta, as long as you keep the relationships of opposite and adjacent correct. In this case, opposite is at the bottom. Adjacent, I don't know. Hypotenuse is 6. Okay, this is why I had you give me the Pythagorean theorem without, just kind of in general. Because I decided to use x. I'm not using a, b, or c. Right, so when I solve for x, we'll set up our equation. Anybody tell me what's my equation plugging in all those numbers into the Pythagorean theorem? Yep.
5 squared plus b squared equals 6 squared.
One more time.
5 squared plus b squared equals 6 squared.
Now, where did you get the b from?
The equation a squared plus b squared equals c squared.
Okay, so in this case, though, I chose not to use those letters, specifically because I think people get in a real habit of using them. So how would you set it up with these letters and
X
numbers?
squared.
Yeah, x squared. I mean, x is what we normally use when we're solving a one-variable equation in algebra. We don't have to, but I just want to make sure everybody understands how to do it without just using the a, b, and c. Okay. So bring the 25 over. What's 36 minus 25? 11. So x is the square root of 11. So since we have a square root, all our rules apply here about leaving square roots in the denominator, things like that. Reducing a square root, if it came out to square root 20, I'd expect something like that to be reduced. So now let's find all of our trig functions. Okay, we already got the sine. What would the cosine be? Yep.
Square root of 11 over 6.
Square root of 11 over 6. Tangent, it's opposite over adjacent. So it's 5 divided by square root of 11. And how would I fix that? So I don't have the square root in the denominator. Sam?
Multiply them both by the square root of 11.
Yeah, multiply top and bottom by what, Justin?
Square root of 11.
Square root of 11. Yeah, so 5 square root of 11 over 11. Okay, so there's our cosine, there's our tangent, we had sine. Well, to get the cosecant, what do I do with the sine?
Just flip the sign.
Yeah, just flip it. We said these are the reciprocals. So the cosecant is going to be 6/5. Okay, my secant, when I flip that, it's going to be 6 over the square root of 11, but then I'm going to have to fix it again just like I did here. So it's going to be 6 square root of 11 over 11. And the last one, my cotangent. Well, that's when you flip the tangent. You got 2 things you could flip. You could either flip the answer we circled or what it's equal to. Which one would be better to flip? Let's save us some time. Yeah?
The original one?
Yeah, the original one. How come?
Well, that way you don't get a square root in the denominator.
Right, that way we don't get a square root of in the denominator. So let's see if I can move those up a little bit. So it should be square root of 11 over 5. If you want to go ahead and flip the other one, you can. You're just going to have to deal with the square root all over again. Okay, so there's all, we had 1 to start with, and there's the other 5, so there's all 6 trig functions of that angle. Okay. Any questions on that? Okay, similar kind of problem. This time they drew it as a picture. Does anybody know real quick what the hypotenuse is? 13. Yeah, how do you know that? Yeah, what's it called? There's a name for that. It's a special triangle. Anybody know what that's called? It's a Pythagorean triple. Okay, Pythagorean triple, there's an unlimited number of them. It's when you have a right triangle and all the sides are integers. 3, 4, 5 is another one. Now, somebody said, well, what about 30, 40, 50? No, 30, 40, 50 is the same as a 3, 4, 5. It's not a different one. It's a Pythagorean triple, but if you just take, like, if you made this 10, 24, 26, that's not a different Pythagorean triple. It's kind of a repeat of this one. Right? But there are an unlimited number of unique, non-repeats Pythagorean triples. Okay? And there's a whole formula for how you can generate them. Okay? And that you can spend a whole hour talking about just Pythagorean triples. It's a lot of stuff. All right, so all we need to do, though, is identify our trig functions. Okay, Lasan, what's my sign? Okay, what's the name of, just give me the name of side 5. That's what? That's opposite, yep. Give me the name of side 12. Adjacent. Let's go back at our trig functions and see which one was opposite and adjacent. Okay, was that sine? No. No, you gave me which one? Tangent. So that's good. We can still write down tangent. It's 5 over 12. But how about the sine? 5 over 13, yes. Okay, the cosine, about Nick?
12 over 13.
Yep, 12 over 13. And once you get the 3 on the left, all we have to do is flip them all. They're all reciprocals to get the 3 on the right. In fact, we've already seen that flipping over and over when you type them in on a graphing calculator. There's no cosecant, secant, or cotangent button. You have to flip them to type them in. Or use some other identity, like tangent is sine over cosine. Okay. Something like that. Or cotangent, cosine over sine. So that's 13 over 12 and 12 over 5. Okay, any one of those 6 equations is enough information for me to find theta. I don't need all 6, I just need one. Especially if you tell me it's an angle in a right triangle. Now you've narrowed down my answer to be between 0 and 90. Because it's acute. Okay, any questions on that? Okay, now I want to look at a couple special angles. We'll look at the 45-90 right triangle and the 30-60-90. Okay, I want to find the 6 trig functions of 45, and I want the exact answers. So if you type this in on a calculator, you're going to get like a 0.707. Okay, I don't want the decimal. I want the exact. Okay, so before I even start to find all 6 trig functions, what should I do first? Find the hypotenuse. Anybody tell me what the hypotenuse is going to be here? Yeah? Yep, square root of 2. It's just 1 squared plus 1 squared, and take the square root. Don't round that off. What kind of triangle is this besides being a right triangle?
It's a 45, 45, 90, or half a square.
Okay, it's a 45, 45, 90, which if you put two of them together, you would get a square. So I guess kind of related to that, what kind of triangle does it have to be if you can put two of them together like that and a right triangle like this and get a square? Yeah.
Equilateral.
It's kind of the idea I'm looking for, but that's not an
Oh,
equilateral.
isosceles.
That's isosceles. Yeah, it's isosceles. When you have an isosceles triangle, you're going to see some of your trig functions repeating. You're going to see some values that are the same. Okay, Julia, what's the sine of 45?
1 over square root of 2.
Yeah. Yep. So you'd have 1 over the square root of 2, which would become,
Square root of 2 over 2.
good, square root of 2 over 2. How about my cosine of 45? Same thing. The opposite and adjacent sides are the same length. So we get the same thing. How about the tangent of 45? Oh, Miranda? Tangent of 45. So what's our definition for tangent?
Opposite over adjacent.
Opposite over adjacent. So what's the side opposite 45? 1. What's the side adjacent to 45?
1.
So when you divide, what do you get? 1. Okay, once you get the 3 on the left, getting the 3 on the right, that's pretty straightforward. All we have to do is flip each of the ones on the left. Flipping 1 is easy. 1 is its own reciprocal. What other number is its own reciprocal? No, if you flip 0, you get undefined. 1 over, you get 0 over 1, that becomes 1 divided by 0, which is undefined. But that can happen, not in this one. What other number do you flip and it stays the same?
-1?
Negative 1. Good. Flip negative 1, stays negative 1. Okay, what's my cosecant and my secant? They're both the same. Andrew?
2 square roots of 2 over 2.
Yeah, 2 square roots of 2 divided by 2, which would be
Square root of 2.
just the square root of 2. Okay, so there's your 6 trig functions for 45 degrees. Okay, I want to find the 6 trig functions of, if we could do 30, we can do 60. We'll see if we do both. Maybe we'll just do one. Using that diagram. How can I do that? Yeah.
You split it in half.
Okay. Split it right down the middle.
Yeah.
All right. So now, what does that do?
Makes it into 2 right triangles.
Right. There are 2 right triangles. And what do you know if you compare these 2 right triangles? There's a name if you compare the 2 of them. Carly?
They're adjacent.
Okay, they aren't next to each other, but so would these triangles be. They're right next to each other. But these are special in a way because they're congruent. There's all kinds of ways you could prove they're congruent. You've got a side matching a side. You've got a side congruent to itself. That's reflexive. And then depending on what theorems you know, if you have an equilateral triangle and you draw in an altitude, it happens to be an angle bisector. So you got side angle side. You could use, we got two right triangles, and we have a hypotenuse and a leg, congruent to a hypotenuse and a leg. That's the HL theorem. So there's all kinds of ways to prove they're congruent. Okay, bottom line, they're congruent. So what does that mean about the length of the bottom of each one of those sides?
It's 1.
It's 1. Okay. Now, if these two triangles are congruent, and originally I said that this whole angle was, well, actually I didn't say, but what is that for an equilateral triangle, that angle? 60. If you break it into two parts, each part would be how much? 30. So what you did is you just created a 30, 60, 90 right triangle, and we can figure out all the sides. We've got the hypotenuse, we've got the leg. Let's find the height. Okay, so when you set up your, or does anybody think they know? Yeah. Yeah, it's square root of 3. 1 squared plus square root of 3 squared gives me 4. Then take the square root. It's 2. Okay, so there's my triangle. And now you can go through and find all the trig functions. Any question on how you would find the sine? All sine, cosine, tangent, secant, cosecant, and cotangent for 30 or 60? No questions if I ask you to do that on a test? With exact answers, not decimals. Just like we did with the 45, 45, 90. I think we already answered that question kind of earlier. It says the two acute angles in a right triangle are complementary. Why? Well, if you have a right triangle and you've got a 90, all the angles have to add to 180. So if one angle is already 90, the other two have to add up to 90, and that's the definition of complementary. Two angles that add up to 90. Okay, so when we start labeling right triangle diagrams, we'll stick with the letters we use in the Pythagorean Theorem for the sides. But for the angles, some books use capital letters and lowercase letters. I think that's how your book does it. I don't like using capital and lowercase letters. Why do you think I try to avoid using something like that?
Because especially when you see a lot, C, lowercase and uppercase looks the same unless you have something to reference it by, kind of. So like certain letters look the same, so it's not helpful.
Yeah, so C definitely, lowercase and uppercase could look the same. Also, if you give me an answer and you say B is 5, if we're using capital and lowercase, then I have to say, well, what do you mean? Do you mean capital B or lowercase b? Well, we're going to avoid that by using Greek letters for the angles and just the regular letters we're used to from the English alphabet for the sides. Does anybody know the name of this angle across from A? What that symbol is called? It is the first letter in the Greek alphabet. Yeah.
Is that a lowercase alpha?
Yep, lowercase alpha. So both the Greek letters you see there are lowercase. That's alpha. And how about the next Greek letter? That's beta. So we always keep B and beta across from each other. Always keep A and alpha across from each other. And keep C as your hypotenuse. And that'll keep everything straight. So I'm not going to do it the way that our book does it. Capitals and lower cases. But make sure you're comfortable with it. I mean, if I give you a question on a test or you see something somewhere else in the book, it shouldn't confuse you. It's just, you got to be more careful when you write your answers. Right, so let's look at one of these angles. Let's look at the sine of alpha. Okay, so you're not going to have any numbers here. This is all letters, but what would the sine of alpha be? What's that?
A over C.
A over C, yep. Opposite over hypotenuse. Now let's look at something different. Let's look at the cosine of beta. Cosine of beta. Thank you.
See the same thing.
Yeah, it's the same thing. The cosine of beta is adjacent over hypotenuse. So the sine of alpha and the cosine of beta, they're the same. Okay, let's look at another one. Tangent of alpha. What's the cotangent of alpha here? Marie?
Opposite over adjacent, so it would be A over B.
Yes, we get A over B. Now I'm going to look at another one. I'm going to look at the cotangent of beta. Okay, what's the cotangent of beta? Yeah, it's the same thing. Cotangent is adjacent over opposite. So from beta, A is adjacent, B is opposite. What's the relationship between alpha and beta? There's a special name for those kind of angles we just talked about. They're what?
Complementary.
They're complementary. Okay? There's also a special name for the way I'm pairing these trig functions. I'm not pairing trig functions with what's across from them, okay, like I did here. I'm pairing sine with cosine. Okay? I could pair secant with cosecant. And then the last pairing does happen to be the same. Tangent with cotangent. So what you're doing is you're pairing up what's called cofunctions. Okay? It's a function. You put the word co in front of it. That's the cofunction. So we'd say the cofunction of sine is cosine. What if I asked you, what's the cofunction of cosine? Sine. Yeah, we'd say cocosine. That doesn't make sense. Okay? So what we've got there, that's a different pairing for your trig functions. Okay? And that's called the complementary angle theorem. Okay? And very simply, that theorem just says that if you take cofunctions of angles that are complementary, the answers always come out the same. Okay, so two things have to happen. One, you've got to have angles that are complementary. 40 and 50, 80 and 10. Okay? Something like that. Two, you have to be given a problem that involves cofunctions. Sine, cosine. Secant, cosecant. Okay, something like that. Okay, so what would that simplify to? Sine of 35 minus cosine of 55. And if you're not sure, first thing I want to know is, are those angles complementary? 35 and 55. Yeah. Are the two trig functions I wrote down cofunctions? Yes. So we have cofunctions of complementary angles. What do we know about these two things we're subtracting? We don't know what they are, but we know they're equal. So what are you going to get? 0. Okay, so the idea with this problem, you don't want to get hung up trying to find what's the sine of 35. I have no idea. What's the cosine of 55? That I don't know either. But I know they're the same. So you subtract two things that are the same, you get 0. How about this one? 1. I don't know what the tangent of 20 is, and I don't know the cotangent of 70, but I do know those are complementary, and tangent and cotangent are cofunctions. So I'm dividing two things that are the same. So it's a special trick that it doesn't come up a lot, but it does come up a little bit. How about that one? 5. I don't know either one of those, but because of the theorem, I know these two are the same. When you divide them, you get 1 times 2 plus 3. Now, could you do that with addition? If you add two things that are the same, do you always get the same answer? No. That works with subtraction, but not addition. How about multiplication? No. If you divide two things that are the same, it's always 1. But if you multiply, no. If you multiply two things that are the same, you get that thing squared, whatever that is. All right, so the homework beyond 361. Okay, so it's 1 to 14. That part's all. 16 to 20 just evens. 21 to 24. And simplify these last two problems, which should be very quick. Okay, so we'll finish up section 6.5 tomorrow, and we'll actually solve triangles using what we learned today.